are surrounded by order. Over the last 300 years, we've developed amazing new ways to harness energy, and we've used this ability to transform our environment. But all these structures that we see around us are just one type of visible order that we've created here on planet Earth. There's another type of invisible order, every bit as complex, that we're only now beginning to understand. It's something that nature has been harnessing for billions of years, something we call information. The concept of information is a very strange one. It's actually a very difficult idea to get your head round. But in the journey to try and understand it, scientists would discover that information is actually a fundamental part of our universe. This film is the story of information and the immense power released from manipulating it.
Good day, everyone. It is a pleasure to see you all here today. We live in a world that is constantly being rebuilt and transformed. We see skyscraper rising, transit system evolving, and entire environment being reshaped by our hands. We often view this as the story of energy, but today, I want to invite you to look beneath that visible surface. I want to talk to you about the invisible order that makes our reality possible. We are going to explore a force that has been harnessed by nature for billions of years. A force that scientists only recently begun to fully grasp. We call it information. Today, we are going to trace the 5,000-year history of how humanity learned to speak the language of the universe. From simple marks on clay to the digital pulse of modern machines. This is the story of how we use symbols, codes, and logic to build structures in a cosmos that is otherwise naturally sliding into disorder. Before we dive into the history, let's frame what we hope to understand today. First, deconstruct the giant leap from pictograms to phonetic symbols and how that allowed human thought to endure across millennia. Second, analyze the Jacquard loom as the definitive birth of programmable technology, separating hardware from software. Third, explain the evolution of information transmission, moving from the speed of matters to the speed of light. And lastly, connect the abstract theories of Turing and Shannon to the very real, physical constraint of the universe, especially why deleting data.
At its heart, writing is all about the transmission and storage of information. Words allow ideas to endure through time. These are some of the earliest texts in existence, and they give us an incredible insight into the development of writing. I've come to meet one of the few people who can still read them, Dr. Irving Finkel. We take writing so much for granted these days that I guess it's easy to forget that it was invented.
It certainly was.
How did it first come about?
The earliest writing that we have is written on clay tablets, and it comes from Iraq, ancient Mesopotamia, and it comes from the culture of the Sumerians. And what happened here was that they started off with purely pictographic signs to express an idea. And this lasted for quite a long time until it occurred to somebody, perhaps accidentally, that what you could do is to make one of these graphic symbols on the surface of the clay, not for what it looked like, but for what the sound it represented was.
So not a picture of an object, a picture of a sound.
That's what we always called the giant leap for mankind.
By combining different sounding pictures, the ancient Mesopotamians could express any idea imaginable. The essence of their breakthrough was to see, for example, that a picture of an eye and a picture of a deer didn't have to mean an eye and a deer. The pictures could be used simply for the sounds they made, in this case, idea. Once this system was discovered, it meant anything that could be spoken, even the most strange or abstract thoughts, could be transformed into symbols. Information could now live outside of the human brain. And this meant it could endure over vast spans of time. It was an idea that fascinated the ancient Mesopotamians.
This lovely tablet here, this king, Ur-Nammu, lived in about 2100 BC, okay? He buried this in the foundations of this temple as a message for the future. This king, Ur-Nammu, the powerful male, king of Ur, king of Sumer and Akkad, so that's the south and the north part of ancient Mesopotamia, her house he built for her, and he even restored it afterwards. So this is a proud thing, and he wants everybody to know about it, and this is a real message for the future.
What's so remarkable for me is that this is information stored on clay for thousands of years.
Yes.
At first glance, information feels straightforward. We use it every day. Our brains are built for it. We trade it in every conversation. Yet, as Jim Al-Khalili points out, information is one of the most subtle concepts science has ever had to grapple with. Think of a library. If you have 1,000 books in a heap on the floor, you have chaos. If you arrange them alphabetically, the physical paper and ink remain identical. But you have created information. This invisible arrangement is our primary tool for fighting against the natural decay of the universe. We are not just moving atoms, we are organizing them. Our journey begins in Mesopotamia with the Sumerians. Writing is, in my view, the most disruptive technology ever conceived. It started as simple pictographs, but the giant leap was the rebel's principle. By using symbols to represent sounds rather than objects, scribes could write down things that didn't have a shape, just like justice, prayers, or mathematics. They fixed the outpourings of the human soul into clay, effectively creating an external memory for our species that has survived for over 4,000 years. For over 4 millennia, writing was only major information technology. That is changed in 1804. Joseph Marie Jacquard designed a loom that could be programmed. This is the critical hardware versus software split. Before this, changing the pattern means rebuilding the machine. Jacquard realized that the instruction could be stored separately on punch card. A hole means leaf, and a blank space means don't. He discovered that if you have a simple yes or no instructions, you can represent any degree of complexity, even a human face in a silk.
Produce about an inch of this amazing stuff. The demand for the fine fabrics of Lyon was immense, but the silk weaving process was painfully slow. But thanks to a soldier and weaver named Joseph Marie Jacquard, a device would be developed to help speed up weaving. In the process, it would reveal a fundamental truth about information. Building on the work of a number of others, in 1804, Jacquard patented his invention. At the time, the loom was the most complex mechanism ever built by humankind. Jacquard's loom was a miracle of ingenuity. You see, he designed a single machine which, without any alteration to its construction, its hardware to use a modern term, could be programmed to weave any pattern a designer could think up. In fact, it could produce a whole range of silk designs with barely a pause in production. Jacquard had found the holy grail of weaving, and his secret was a simple punched card. The punched card held within it the essence of the designs that the loom would weave. When these punched cards were fed into the loom, they would act to lower and lift the relevant threads, recreating the pattern in silk. Any design you could think of could be broken down and translated into a series of punch cards and could then be woven by the loom. Information was being translated from picture to punch card to the finished fabric.
It is a machine for weaving textiles, that's its task. But there is nothing specific about what textile it should weave. That is contained in the information which is encoded on the cards. So if you like, the cards program it, that is to say, instruct it what to do. And this has huge resonances for what came later.
Jacquard's loom revolutionized the silk industry, but at its heart was something deeper, something more universal than its industrial origins and its ability to speed up weaving. The loom revealed the power of abstracting information. It showed that you can take the essence of something, extract the vital information, and represent it in another form. Writing had revealed you could use a set of symbols to capture spoken language. Now, Jacquard had shown that with just two symbols, a hole or a blank space, it was possible to capture the information in any picture imaginable. This is a portrait of Jacquard that's been woven in silk. It's spectacularly detailed with hundreds of thousands of stitches. And yet all the information you need to capture this lifelike image can be stored in a series of punched cards, 24,000 of them to be precise. This picture is a fantastic example of a really far-reaching idea. That the simplest of systems, in this case cards with a series of holes punched in them, can capture the essence of something much, much more complicated. If 24,000 punch cards could create an image like this, what would happen if you had 24 million or 24 trillion cards? What new types of complex information might be able to be captured and represented? Jacquard had stumbled on an incredibly deep and far-reaching idea. As long as you have enough of them, simple symbols can be used to describe anything in the entire universe. Translating information into abstract symbols to store and process had proven to be an extremely powerful idea. But the way information was sent, the way it was communicated, hadn't changed for thousands of years.
The world before telecommunications technology was a very different place because you could only send messages as fast as you could send objects.
Until the 1840s, information was heavy. It could only travel as fast as the person or a ship. Samuel Morse and Alfred Bell changed the medium from matter to electricity. They didn't just invent a machine, they invented an efficient language by giving common letters like E the shortest pulses. They optimized communication. This made information unimaginably lighter, allowing us to bind the entire planet in the latest of wires and transmit data at the speed of light. In 1936, Alan Turing introduced the paper tape model. He showed that a stream of symbols, ones and zeros, could act as mechanical instructions. His logic was revolutionary. Calculation is not thinking. It is a mechanical process of following rules. He defined the universal machine as a device that can perform any task if fed the correct information. This is why today, one device, your smartphones, is able to replace a camera, a map, and a telephone.
My goal in building this project was to create a machine that embodied the classic look and feel of the machine presented in Turing's 1937 paper on computable numbers. At the heart of the machine is the read-write head. It has the ability to write, read, and erase from the tape. Writing on the tape is done with a standard fine-point dry erase marker. The marker is moved in the y-axis with a servo. The transport of the tape provides the x-axis motion. The marker is lowered and lifted from the tape with an additional servo. Erasure of the tape is accomplished with a felt-covered cylinder. A small gearhead DC motor rotates the cylinder through a toothed belt and pulley system. The erase head is lowered and raised by a small pin in the base of the read-write head. This pin rides on a cam attached to a servo. To read the characters on the tape, a TSL 1401 line scan camera is used. This camera captures a single row of 128 grayscale pixels. By transporting the tape between scans, a complete character can be recognized. A bank of LEDs provides even illumination for the camera. This camera provides the only source of information the Turing program has for what is on the tape. The tape for the Turing machine is a 1,000-foot roll of white 35mm film leader. Motorized roll stands at either side of the read-write head automatically handle the tape. Transport of the tape is done with the cog at both ends of the read-write head. These cogs are moved with a stepper motor driving a tooth belt system. One revolution of this motor is equal to one cell of the tape. Just in front of the read-write head is the control console. This console contains a custom display board. Mounted to the back of the display board is a second PC board containing a parallax propeller chip. The propeller chip provides all the control for the machine. Adjacent to the propeller board is a third PC board that provides power and control to the servos and motors. The control panel of the machine gives you access to all of its functions. Through the use of a 5-position switch, you can load programs, define defaults, move and erase the tape, or run in single step through programs. Programs are written and saved to SD cards as simple text files from any computer. Once the card has been inserted into the machine, you can browse its directory and select the program you want to run. Often programs need to operate on a tape that already contains data. Default tapes can be saved as part of a program file. They can also be created and edited from the user console. Once a program has been loaded, it is started from the console. In this example, the machine is running a simple binary counting program. First, the default starting data is written to the tape. After the default tape is written, the tape is returned to the first tape position, and control is turned over to the Turing transition rules that were loaded from the SD card. While the program is running, 3 LED displays provide feedback. This includes the current machine state, the tape position, and a running count of the operations completed so far. Additionally, the 4-line LCD display shows the transition rules that apply to the current machine state. Each loop of the Turing program reads the current cell from the tape and uses the transition rules to determine if that cell of the tape needs changed. If it does, the cell is erased and written with the new character. It then changes the state of the machine if needed, and the loop starts again. In this simple binary counting program, the binary number is incremented each time the tape makes a full transition from the least significant bit to the most significant bit and back again. In this example, the machine is counting from 11 to 16. Because it takes 50 operations to do this, I have sped up the video to save time. When the machine reaches a halt state as defined in the transition tables, the Turing program exits from its loop and control is returned to the console. Thank you for watching this video. I hope you have enjoyed it.
In 1948, Claude Shannon defined information as unexpectedness or surprise. If a message is expected, it contains no information. He gave us the universal unit of measurement, the bit or bit, or binary digit. A bit is the smallest unit of discrimination between two states, such as on or off. Because of the universality of the bit, any message, be it sound, image, or text, can be reduced to a string of ones and zeros and transmitted anywhere.
Out how much tax to charge. Observatories hired them to calculate navigational data. Human computers were vital to the modern world, dealing with the huge amounts of information produced as science and industry grew ever more complex. What Turing did in his 1936 paper was ask a simple but profound question. What goes on in the mind of a person carrying out a computation? To do this, he first had to discard all the superfluous details so that only the very essence of the process of computation remained. So, first off went the ink pot, then the pen, then the slide rule, then the pencils and the pads of paper. All these things made it easier, but none of them were absolutely crucial to the person carrying out the computation. Now Turing asked, what goes on in the brain of a human computer? It's a vastly complex biological system, capable of consciousness, thoughts, and insights, but to Turing, none of these was critical to the process of computation either. Turing realized that to compute something, a set of rules had to be followed precisely. That was all.
He takes the higher level intelligence that was presupposed to be involved in calculation, which is thinking, and says you can have a mechanical process, that is, and by mechanically means an unthinking process, to perform the same act, and therefore eliminates the necessity of human agency with all its high level functions. And that is what is revolutionary about what he tries to do.
Turing's brilliant mind saw that any calculation had two aspects: the data and the instructions for what to do with the data. And this will be the key to his insight. Turing had to find a way of getting machines to understand instructions like add, subtract, multiply, divide, and so on, in the same way that humans do. In other words, he had to find a way of translating instructions like these into a language that machines could understand. And with flawless, impeccable logic, Turing did exactly that. This may look like a random series of ones and zeros, but to a computing machine, it's a set of instructions that can be read off step by step, telling the machine to behave in a certain way. So while a human computer could look at this symbol and understand the process that was required, the computing machine had to have it explained like this. This paper tape that Turing envisaged is what we would now call the memory of the computer. But Turing didn't stop there. Turing realized that feeding a machine instructions in this way had an amazing consequence. It meant that just one machine is needed to perform almost any task you can think of. It's a beautifully simple concept. In order to get the machine to do something new, all you had to do was feed it a new set of instructions, new information. This idea became known as the universal Turing machine. The more you wanted your machine to do, the longer the tape had to be. Bigger memories could hold complex, multi-layered instructions about how to process and order any kind of information imaginable. With a big enough memory, the computer will be capable of an almost limitless number of tasks. This idea of Turing's, that a multitude of different tasks can be carried out simply by giving a computing machine a long sequence of instructions, is his greatest legacy. Since his paper, Turing's dream has been realized. So calculations, making phone calls, recording moving images, writing letters, listening to music, none of these require bespoke machines. They can all be carried out on a single device, a computing machine. This phone is a modern incarnation of Turing's amazing idea. Inside here are many, many instructions, what we'd call programs or software or apps, that are nothing more than a long sequence of numbers telling the phone what to do. What's amazing about Turing's idea is its incredible scope. The sets of instructions that can be fed to a computer could tell it how to mimic telephones or typewriters. But they could also describe the rules of nature, the laws of physics, the processes of the natural world. This is a simulation of many millions of particles behaving like a fluid. To work out how it flows, the computer simply follows a set of instructions held in its memory. This only begins to hint at the power of computing machines. This is a computer simulation of the large-scale structure of the entire universe, and it reveals the true power of Turing's idea. Turning instructions into symbols that a machine can understand allows you to recreate not just a simple picture or sound, but a process, a system, something that is changing and evolving. By manipulating simple symbols, computers are capable of capturing the essence, the order of the natural world itself. By thinking about how the human brain processes and computes information, Alan Turing had had one of the most important ideas of the 20th century. The power of information was revealing itself. It would be very easy to think that after Turing's ideas were made real, the true power of information would be unleashed. But Turing was only half the story. The modern information age would require another idea, one that would finally pin down the nature of information and its relationship to the order and disorder of the universe. It was an idea that would be dreamt up by a gifted and eccentric mathematician and engineer. Claude Shannon was a true maverick, and his desire to tackle unusual...
We conclude with the deep relationship between information and physics. James Clerk Maxwell imagined a demon who could create order by observing molecules seemingly for free. The solution discovered by Rolf Launderer is that the demon's brain is finite. To keep working, he must delete all data. Deleting information is a physical act that releases heat. This tells us something profound. Information is not an abstract ghost. It is a physical, it is bound by the laws of thermodynamics. And it is a fundamental part of the fabric of our universe. Whether we store it in a clay of quantum chip, information is the paintbrush we use to build order of chaos.
And that's because even the most insignificant event contains a spectacular amount of information. Let me show you. Imagine how many bits of information you would need to describe this. the beautiful and intricate interplay of physical laws taking place at scales and time frames that are normally imperceptible to us. But here, you're still only seeing a fraction of the complexity of nature. Imagine the interplay between the trillions upon trillions of atoms. The amount of bits you would need to describe this is almost unimaginable. But what's amazing is that now, thanks to the ideas of Turing and Shannon, we're able to describe, model, and simulate nature in ever greater detail. But this isn't the end of the story. Information, it seems, isn't just a way of describing reality. In the last few years, we've discovered that information is actually an inseparable part of the physical world. It's a really difficult idea to get to grips with, but information, everything from a Beethoven symphony to the contents of a dictionary, even a fleeting thought, all information needs to be embodied in some form of physical system. Amazingly, the reason we understand the true connection between information and reality is because of Maxwell's demon. Remember, it seemed like the demon could use information to create order in a box of air that started out completely disordered. Moreover, it could do this without expending any effort. Information seemed to be able to break the laws of physics. Well, that's not true. It can't. The reason why Maxwell's demon can't get energy for free lies here, in his head. What was discovered was this. The demon really is using nothing more than information to create useful energy. But this doesn't mean that he's getting something for nothing. Remember how the demon works. He spots a fast-moving molecule on one side of the box, opens a partition, and lets it through to the other side. But each time he does that, he has to store information about that molecule's speed in his memory. Soon, his memory will fill up, and then he can only continue if he starts deleting information. Crucially, this deletion would require him to expend energy.
The demon needs to keep a record of which molecules are moving where. And if the record-keeping device is only finite size, at some point the demon's going to have to erase it. That's an irreversible process that increases the entropy of the universe. It's the erasure of information that increases entropy once and for all.
What was discovered is that there's a certain specific minimum amount of energy, known as the Landauer limit, that's required to delete one bit of information. It's tiny, less than a trillionth of the amount of energy in a gram of sugar, but it's real. It's a part of the fundamental fabric of the universe. Amazingly, we can now do real experiments that test aspects of Maxwell's idea.
To wrap up, we have seen that every aspect of the physical world can be taught as a blank canvas. We are currently at the beginning of our journey to unlock the true power of information. As we develop new ways to store it, using DNA or quantum particles, we are effectively learning to be better architects of reality itself. Thank you for your time. I'm happy to open the floor for questions.